In this video, we're going to keep talking about the normal curve and why we like it and like to sort of generalize data to it. And the big reason comes back to this notion that's sometimes referred to as the empirical rule. Sometimes you'll hear it called the 68, 95, 99.7 rule. And it's this idea that certain amounts of the data, if it's on a normal distribution, are going to fall within a certain fixed amount of standard deviations from the mean. What we mean by that is here we have our mean right here in the middle of our data. And if we look one standard deviation away on either side, 68% of the data is going to fall in that window. So over half of the data is going to fall within one standard deviation of the mean. So we know, given this empirical rule, that 68% of the data will fall within one standard deviation of the mean. And so that means like you get a really good sense of what's going on with the numbers. And then we can even generalize that a little more if we move a little further out from there. Notice at 2 standard deviations, so from here to here, within 2 standard deviations then, we get 95% of the data. That means almost every single piece of the data is going to fall in that window. And so why that really matters is we typically will think of any value that's outside of that 2 standard deviation range as an outlier. So anything that is more than 2 standard deviations away from the mean is going to be an outlier. Or anything that's sort of below, any data 2 standard deviations below, it helps if I can spell below, is also considered an outlier. And so we sort of view this sort of outside area here as our outlier area because such a small percentage of the data falls in that window. Now, there are some people who would argue that outliers truly need to be more than 3 standard deviations away, because basically 99.7% of the data is going to fall within 3 standard deviations. So that's what when I say, like, back on the previous example, we didn't bother making a 4th standard deviation because we're talking 99.7% of all the SAT scores are going to fall between 409 and 1711. The chances of something falling outside of that is so infinitesimally small that we don't even worry about it. Now, we can actually break down that empirical rule a little more to sort of help us sort of make some predictions about what chunk of the data should fall in certain ranges. And so what sometimes you'll see people do is on their normal curve, they like to sort of add in little lines where each standard deviation falls. And so we're told that 68% of the data is between, one standard deviation away. Well, a thing about a normal curve is it's equally distributed, which means half of that 68 needs to fall above the mean and half of it needs to fall below. Well, half of 68% is 34%. So 34% would fall between the mean and 1277. And 34% of the data, of the scores, are going to fall between 843 and 1060. And so we can sort of keep doing this and filling in pieces. So it's like we know that 95% of the data needs to fall in that next level between, the 2nd and 3rd standard deviation. And, we've already used 68%, which leaves 27% for these 2 little spaces. Divided in half would be 13.5%. And so notice I'm just sort of filling in little pieces in left. And then technically everything above 2 standard deviations would be 2.5% on either side, but we can actually get a little more precise than that. And so I'm just going to fill in those numbers. So between the second and third standard deviation, that would actually be 2.35% of the data, and anything above would be 0.15%. And keep in mind, this isn't, in every set of data in reality. It's an estimate. We're approximating data, but it gives you a really good general sense of what's going on. So what sort of questions do we do with this percentage stuff? Well, some things that people want to know is that if they go back and they might say, okay, I want to know what percentage of scores fall below a certain amount. Given this score, how many students who took the SAT probably scored below it? And so we're going to start with that 843. So if you remember, this value was 1 standard deviation below the mean. So if we go back up to our sort of curve here, we're looking at the 3 sections sort of here. The 13.5%, the 2.35%, and the 0.15%. So if I want to know the percentage of scores that fell below, I could simply add up those 3%, and I would find that 16% of the data fell below that value. And that's one strategy for dealing with this. So if I know that empirical rule breakdown, I can sort of add my pieces together. Similarly, looking at this next one, if I wanted to know what percentage of scores fell between 626 and 1277, remember 626 was 2 standard deviations below the mean, and 1277 was 1 standard deviation above the mean. Well, 1 standard deviation above the mean, between the mean and that, was 34%. 2 standard deviations below would be that 34% plus the 13.5. And if I add all these together, I would get 81.5% of my data fell between those 2 points. So the empirical rule gives us a way to sort of figure out approximately how many students would fall in that range. Now, we run into issues if we're given something like this problem below here where it says, all right, to get an ASU, an Arizona student needs to score at least an 1120 on their SAT if they're using SAT data. What percentage of scores of the people who took SATs fell into that range? That's not one of our numbers that is like a nice even standard deviation away. So when we're not an even standard deviation away, we're going to actually need to use a calculator. And for this one, we're going to use Desmos. And so I'm going to flip over to Desmos for a minute so that you can sort of see how normal distributions work in Desmos. And we're actually going to use Desmos to go back and double check our answers on C and D as well. So first, let's get our normal curve into Desmos. So there's a few different ways you could do this. You could type it in, or if you go to functions and underneath distributions, you will see something called normal distribution. Now, I would recommend naming it for this because as we'll find out later, there's some things that will help you if you name your normal distribution. So I'm putting A equals, that's just going to be the name of my curve. Then you have to type in the mean and then the standard deviation. So in this case, our mean was 1060 and our standard deviation was 217. Oops, helps if I write in the right number, 217. Now, you might be looking at my graph and going, I don't see anything. I just see a random line. So just like with the other data displays we did in Desmos, if you hit that magnifying glass, it zooms into what it should look like. And so, ooh, look at that nice little thing. You know, I'm going to sort of change it a little, but all right. I got a sense of what my curve would look like. Now, what we're doing here is we're actually finding the cumulative probability. We're looking at sort of what's the likelihood that, you know, a data falls within a certain range. Now, we can do different things. So let's just, you know, do some of the ones that we did before. You'll notice right now it has a minimum of -1,000 and a maximum of infinity and a max of infinity. Basically, everything under the normal curve has a value of 1 because there's 100% probability that something falls under this curve. The data point does. So this is going to pop out probability in a decimal form. We then are going to turn it into a percent. That should be something we're good at doing by now. Now, if we go back to that question C for a minute, and so I'm going to open that back up. Remember, we were asked what percentage of scores fell below 843. So that would be a sort of max value. I want 843 and then everything below it. So if you notice here, the graph sort of shows you the shaded portion, and then a decimal value pops up, and it's 0.1586. And if we rounded that, because our empirical rule does round, that would round to about 16%. And so 16% of the scores fall below that value, and notice the shading falls below. Now, the next question asked what set of scores fell between 626 and 1277. So this time I'm going to take out that minimum and I'm going to put in the 626 and I'm going to change my maximum to that 1277, and I'll notice 81.8, and rounding errors with the empirical rule. So about 81% of the scores, 82% of the scores fell between those two values. We're doing pretty good. Now, if you wanted to use this calculator instead of the empirical rule, that would be 100% okay on these types of problems. In fact, once you get good with sort of using this tool, it makes it almost easier, and plus it then comes with that nice nifty visualization. All right, so let's get back to that ASU question. So ASU was asking what percent of the people who took SAT in 2021 scored high enough to get into ASU. So in this case, we don't have a max value, we have a minimum value. It was that SAT score, which was 1120. And if you look here, my minimum score of 1120, and I notice, okay, that's 0.391. Well, remember, we don't want 0.391. We want it as a percent. So to turn it into a percent, we would multiply by 100, and that would become 39.1% of the students got scores above that sort of cutoff score. Now, what do I do with these percents? That's not actually telling me how many students scored that amount. It's telling me what sort of likelihood, like about that many, would probably score above. However, we can keep going a little further with this. If we know that 1.5 million students took the SAT, then how many got that score? Well, this is just sort of a percent of a total question now. If I have 1.5 million, that's 1500000, and then I times it by my decimal form of my percent, I would find that 586,624 students scored an 1120 or better according to this normal distribution. If you click on to the next slide, you're going to get an opportunity to practice sort of using a normal distribution calculator, and then keep going, and we're going to learn how to sort of figure out if something is an outlier using our normal curve.